All right. Happy Monday, everybody. I hope you all had a nice weekend. Can you guys see me and hear me and see my slides? Awesome. Wonderful. Thank you. All right. So today we are, as you guys might have guessed, going to keep on trucking through chapter 8, the reactions of alkenes. A couple of super quick announcements for you guys. I have indeed posted your Achieve homework for chapter 8. And notice this is a shift. We are probably going to need Friday to finish up chapter 8. So I've already gone ahead and pushed our Achieve chapter 8 deadline for homework until Monday morning, 9 a.m. on 1 week from today. We are also going to have a quiz on chapter 8 on that same Monday during class. So we should finish up chapter 8 during the first part of the day on Friday and start in on chapter 9 on Friday. But chapter 8 will be quizzed on Monday during class. I have not posted your quiz grades from last week, but those should be up shortly, hopefully before the end of the day today. All right, so we have been going through chapter 8, and yes, I will also release exam 2 answers for you guys soon. So we've been going through chapter 8, which is, again, the reactions of alkenes. And we've gone through sort of the first couple of things. And just as a reminder, I'm not going to talk about addition to HX today, but we spent some time on this last week. And you guys now know 2 different methods for addition of HX across double bonds. You know, electrophilic HX addition, which you can use any halogen for, that gives Markovnikov addition. And you also know HBr addition, where we add in these peroxides to switch the mechanism to a radical mechanism and get you to an anti-Markovnikov product. So those are the 2 forms of HX addition that you know. We started in on hydration last week, and I will pick up from where we left off with hydration and carry through the next couple of bullet points here. Just as a reminder though, most, not all, but most of our alkene reactivity is going to stem from the fact that we have pi electrons that are loosely held in that pi bond, and so they can act in a nucleophilic manner to attack an electrophile and form a new carbon electrophile bond, often sort of transferring that electrophile nature to somewhere else, usually the other carbon of the alkene. And so this is this first step of these pi electrons acting as a nucleophile is by far going to be the predominant reactivity mode for alkenes in most, but again, not all of the reactions that we'll see in chapter 8. So like I said, today we're going to pick up with hydration. We covered this in a good bit of detail on Friday, but we're going to extend it a little bit further today. So as a reminder, on Friday and for part of last week, we talked about the hydration of alkenes using dilute sulfuric acid, which goes in a Markovnikov fashion. So what do I mean by all of this? So the dilute sulfuric acid means that we have a lot of protonated water around. This proton comes from that sulfuric acid. And in a mechanistic sense, our pi bond electrons will act as a nucleophile to grab that proton, and that will form a new carbon proton bond or carbon hydrogen bond on the less substituted carbon, because you will be generating a free carbocation on the more substituted carbon. And it is this very first initial step, the location of that new carbon hydrogen bond, that dictates that this is a Markovnikov addition product because of this carbocation being on the more substituted carbon. Once you get to this position, you have this carbocation, which is now electrophilic. So more water, you're in dilute H2SO4, so you have plenty of water around, and that water does indeed act as a nucleophile to form your new carbon oxygen bond that gets you to your product after a deprotonation step. And notice in your product, we've now added water. Here's the OH of water, and here's the H of water. We've added water across the double bond, and again, this goes in a Markovnikov fashion. So we talked about this in good detail. I've noted that it's exactly the reverse of an E1 elimination or a dehydration. So our hydration is exactly the mechanistic reverse of a dehydration. But I also noted last week that these are highly prone to rearrangements because of this free carbocation. And they're also very prone to side reactions because sulfuric acid is not a nice, friendly, calm, mild reagent. It's actually pretty harsh and can do damage in other parts of the molecule if you have any sensitive pieces in your molecule. So because of this, we as chemists are going to try to figure out a separate way to effectively add water across a double bond in a Markovnikov fashion, but without using sulfuric acid and without generating a carbocation intermediate. All right. And in terms of the arrows here, someone's asked to have me explain the arrows again. These arrows follow a very traditional electrophilic addition mechanism where nucleophilic pi electrons reach out and attack our electrophile. In this case, that's a proton, forming our new carbon-hydrogen bond here and leaving behind a carbocation here. That carbocation, same carbocation as up here, can be attacked, right? It's now an electrophilic carbocation. So the lone pair of another water molecule can go in and attack at that electrophilic site to form a new carbon-oxygen bond. And then if we follow all of our electrons exactly, we would have to deprotonate that intermediate. So we're going to take another molecule of water and use the lone pair of that water solvent molecule to deprotonate our intermediate to give you our final product, which has the OH of water added on one side, the more substituted side, and our second H of water added on the less substituted side of the double bond. Okay, so like I said, these are prone to rearrangements and side reactions. And so therefore, we're going to come up with another method to do this. And I introduced this on Friday, but I know it was towards the end of class, so I want to go over it fully in detail again here. And that is called oxymercuration demercuration. So this is kind of a two synthetic steps that are often done in sequence. And the reason we're going to do this is because that hydration I was just talking about with sulfuric acid doesn't work very well in real life. And so chemists have come up with a different way by using this mercuric acetate reagent, which dissociates to give an active reagent that has lost an acetate and is this positively charged mercury reagent. And we're going to do in this first step oxymercuration. So we've had an oxygen added to one side of the double bond and a mercury added to the other side of the double bond. So it's an oxymercuration. And then we're going to take our new mercury carbon bond and replace it with a carbon hydrogen bond in a step called demercuration using the reagent sodium borohydride. And so I'll explain each of these individual synthetic steps over the next couple of slides in mechanistic detail to keep everybody up to date. But just again to point out, the reason that we're going to do this is because these are milder conditions than using the sulfuric acid method of hydration, and it avoids rearrangements, and it also avoids the possibility of polymerization, because if you create a carbocation intermediate, another molecule of the alkene could act as a nucleophile on that carbocation intermediate to polymerize your initial substrate. Okay, so let's focus on the oxymercuration step. In the oxymercuration step, we're going to take mercury acetate, and it's going to dissociate to form this positively charged active electrophile. So this mercury acetate with a positive charge is the active electrophile, and that's what's going to add to the pi bond. And it adds in a fashion that you would typically expect, where this process is initiated by those pi electrons attacking as a nucleophile this electrophilic mercury. Now, this electrophilic mercury also has some lone pairs of electrons on it. And so that lone pair of electrons will at the same time form a new a new mercury carbon bond with the other carbon of the double bond. So we've created a 3-membered ring intermediate. This is called a mercurinium ion. It still has its positive charge because we're combining a neutral species with a positively charged species. So we haven't lost any of our charge. We still have a positive charge. And what we've done is we've taken 2 electrons from our pi bond, 2 electrons from our mercury, and we've made 2 new sigma bonds, both between the mercury and between each carbon of that former double bond. So from this positively charged intermediate, because it is still electrophilic because it's positively charged, our water molecule, which is prevalent because it's our solvent, our water molecule can act as a nucleophile and attack at one of the carbons that used to be a double bond carbon, and then break that carbon-mercury bond associated with that carbon. And after a deprotonation step, we get to the intermediate of this process, which has a new carbon-oxygen bond, a carbon-mercury bond, just one now instead of the two of our previous intermediate. And so now we've completed the oxymercuration step of this sequence. I just want to point out, there are no free carbocations here, right? We have not ever generated a carbocation. And so there's never been a chance for our intermediates to rearrange along the way. They've always been trapped and stored in kind of safekeeping in this the mercurinium ion three-membered ring. Okay. In the second step of this sequence, we have sodium borohydride as a reagent, which is going to be a source of H- or a hydride, which is a hydrogen atom carrying 2 electrons, so it has a negative charge. This hydride can attack at this carbon atom and basically displace the mercury reagent. So the H- is going to come in and displace mercury, so you get a new carbon-hydrogen bond in the same location where you had a carbon-mercury bond. So this is the second step of the sequence. Overall, after we've done our oxymercuration and our demercuration, you can see that we have added a hydroxyl group, an OH on one side of the carbon that used to be a double bond, and a hydrogen on the other side of the carbon that used to be our double bond. And so overall, this is indeed the addition of water across a double bond as the overall reaction product. So not as the mechanism, right? But as the overall reaction product, we have added a molecule of water across our double bond. Now, it turns out this OH group came from water, but this hydrogen actually came from sodium borohydride, right? So, but overall, we've added a molecule of water effectively across our double bond, and we've done so in the Markovnikov orientation, where our electrophilic side is the less substituted side, right? And that counts whether you count your electrophile as the mercury or as the hydrogen. And our OH has been added to the more substituted side. So it is indeed a Markovnikov product. Okay, I want to drill down a little bit deeper on that Markovnikov orientation, and let's make sure we really understand why and how that is the case, because I haven't actually convinced you of that, in my opinion. So I'm gonna try harder to convince you of that right here. So if we have a double bond that is more substituted on one side than the other, then in this first mechanistic step of oxymercuration, we make our three-membered ring, our mercurinium ion, our three-membered ring. And on the previous slides, I've kind of shown it as if these bonds are all created equal, but they're not. These bonds are not created equal. And so what happens here is that the carbon of the double bond that is more substituted has a weaker bond with mercury. And that should make sense because that carbon is better able to support a delta positive charge. And so that bond is going to be weaker with mercury. Now, what that means is that when the nucleophile attacks, that nucleophile is going to attack on the side of that former double bond that has that more positive charge buildup. So our nucleophile will come in to the more substituted side of our mercurinium ion, and it'll break this carbon-mercury bond with the 2 electrons that are here going back to the mercury, because otherwise we would have more than 8 electrons at that carbon. When we take that step, we have a new carbon-oxygen bond, again, on the more substituted carbon of our double bond. And the only remaining bond between carbon and mercury is left on the less substituted carbon of our previous double bond. And so this is the Markovnikov orientation. This is what sets that orientation. And you can see, in this case, our mercury is our electrophile, and our electrophile is indeed on the less substituted carbon of our double bond. Okay, so we're almost done. We still have to take our Markovnikov product, right? Our product of our oxymercuration. And we have to do a demercuration, and that's done again with sodium borohydride, where this hydride addition basically displaces the carbon-mercury bond and replaces it with a carbon-hydrogen bond. All right, couple of reminders. There are no rearrangements here. We have not created ever a discrete carbocation in this process, and so we do not have rearrangements. And just as a reminder, this is the benefit, because if you recall back to Friday's slide, we tried to do this same hydration on this same substrate. I've drawn them a little differently here, but these are the same two compounds, 3,3-dimethylbutanene. And when we try to do our acid-mediated hydration on this compound, we end up with our hydroxyl group all the way over here instead of on one of the carbons of the double bond like we had intended. And so this rearrangement is why we had to come up with these new reagents, this oxymercuration, demercuration sequence, is to avoid situations like this where our hydroxyl group ends up on a rearranged carbon scaffold. Okay, so the last moment, the last kind of feature of oxymercuration, demercuration is kind of cool. What we're going to do is take what we already know about oxymercuration, demercuration, and we're going to extend it just a little bit and see what happens if instead of doing this reaction in water, we do it in an alcohol solvent. So we're just changing the solvent. Instead of water, we're going to do it in an alcohol solvent like methanol or ethanol. Now keep in mind, water is actually an alcohol solvent also, right? It's just a specialized alcohol where it's two hydrogens instead of a hydrogen and a carbon. But in our alcohol solvent, so if we were going to do this reaction in methanol or ethanol instead of in water, we would come to the same three-membered mercury intermediate, our mercurinium ion. And instead of water oxygen lone pair acting as a nucleophile, our alcohol lone pair would act as a nucleophile. So it would attack the more substituted carbon, because that's where that delta plus is, break our carbon-mercury bond there, and get us to a situation where we now have a new carbon-oxygen bond, just like in the case of water. We still have our carbon-mercury bond. And then after we deprotonate, what we're going to get is an organomercurial ether instead of an organomercurial alcohol. So when we do this reaction in water, we end up with an OH as our new bond, because we had H2O. If we do it in alcohol, we're going to end up with OR as our new addition because we did it in HOR. The demercuration step works just like it did before. We take our sodium borohydride and we swap out our mercury with a hydrogen atom. All right, there's a comment in the chat box. So the question is, would the mercurinium ion having a weaker bond with the more substituted carbon also have something to do with steric hindrance? That's a great question. The answer is probably, but it is more so having to do with the electronics of the more substituted carbon being more delta positive there. But yes, sterics could play a role there as well in kind of lengthening that carbon-mercury bond. It's probably more so the electronics. Okay, so now we know how to do what's actually an alkoxymercuration, demercuration, where instead of just an OH here, we end up with an OR here. And so now we can try to apply this. So I posted this question with the slides from class on Friday. How many of you actually tried it? Right? You don't have to raise your hands or answer that. I'm guessing not that many of you tried it. It was beautiful weather this weekend. So, we're going to do it together. You don't need to turn this in. So this isn't for us to do an upload. But what I'm going to do is walk you through each step of this question. And I want you guys to follow along with what I'm doing, but also really try to be thinking about it on your own and using your own knowledge of what we've just gone through to be trying to guess at what I'm about to say even before I say it. So the question here says, show the intermediates and products that result from alkoxymercuration, demercuration of 1-methylcyclopentene using methanol as a solvent. So here is our 1-methylcyclopentene, and we're going to be doing an oxymercuration, demercuration, but we're going to do it in methanol, not in water. And I gave you guys a hint, right? Be sure to review the last 2 slides. And so just as a reminder, over the last 2 slides, here are the things that we've learned. We have learned that the bonds of that mercurinium ion are not equivalent, and that because the bond between carbon and mercury on the more substituted side is weaker, that is where the oxygen is going to attack. We've also learned that oxymercuration, if you do oxymercuration in an alcohol solvent, you generate an ether instead of an alcohol. So let's apply those 2 things and let's try to answer this question together. So what's our first step going to be? Our very first step is going to be, as it is with most reactions in this chapter, using those pi bond electrons in a nucleophilic fashion. So in our first step, we're going to generate our mercurinium ion, our 3-membered ring with 2 new bonds to mercury and with a positively charged intermediate. So now I'm going to also use this time to show you guys and go through mechanistically what's happening here. So to get to this intermediate that I'm showing here on the right, we're going to take our pi bond electrons and they're going to attack our electrophilic mercury center. And then as noted, that mercury has a lone pair that can then at the same time go back in and attack the more substituted carbon of our double bond. So we'll create a 3-membered ring here, and 2 new sigma bonds to mercury are being made with the 2 pi electrons from our alkene and also 2 electrons from a lone pair from mercury. The next thing that we're going to do from this mercurinium intermediate, we can now, this is an electrophilic species, and we can now have our alcohol solvent act as the nucleophile. So the lone pair on our alcohol solvent is going to attack one of the 2 carbons that used to be part of the double bond. And the way it's going to decide which way to go is that it's going to go towards the more substituted one, because that's the side that has the weaker carbon-mercury bond. So our lone pair of electrons from our oxygen is going to attack here at this more substituted carbon of the mercurinium. And that's going to break that carbon-mercury bond, because otherwise we'd be giving oxygen more than 8 electrons, or sorry, we'd be giving carbon more than 8 electrons. We know we can't do that. And so those 2 electrons that were in the sigma bond between carbon and mercury on the weaker side, those 2 electrons will go back to that mercury ion and break that bond. And that gets us to our kind of precursor to the oxymercuration product. It still needs to be deprotonated, so let's go ahead and do that real quick. We will have a lot of methanol around because it's our solvent. So we can take our methanol, another molecule of methanol, and the lone pairs of that oxygen can act to deprotonate our intermediate. And then that would give us our oxymercuration product. So on the next slide, I'm going to show you the oxymercuration product, which looks like this. So this is the same molecule I had at the tail end of the last slide. It has just been deprotonated as we showed with those mechanistic arrows on the last slide. So we've completed oxymercuration, right? You can see we've got our oxygen addition and our mercury addition. So we've done an oxymercuration. So now we need to do a demercuration. And the way we do that demercuration is by using the sodium borohydride reagent, which again acts as an H- or a hydrogen atom with 2 electrons. And these 2 electrons are going to act in a nucleophilic manner, and they'll attack at that carbon and displace that mercury. And when they do that, you will achieve our final product here, where you can see I've drawn this out so that the new hydride that was added here, our new hydrogen atom, is black because the sodium borohydride I used was black. So I'm color coding here so you guys can follow along. And you can see also this red hydrogen was already there. It was one of the implied hydrogens from our original substrate. But you can see what we've done overall is added methanol across our double bond. And we've done so in a Markovnikov way, where our oxygen bond is on the more substituted carbon, our hydrogen bond is on the less substituted carbon. So that's the oxymercuration, demercuration in full sequence and in a drawn out example. And if you guys don't have any questions, I'm going to move on to the next topic for chapter 8. And I'll post these slides. I'm going to post all of these slides, including all of my drawings. So you guys will be able to see all my drawings when I post the slides. Okay, so I'm going to move on now to a new type of reaction called hydroboration. And in our hydroboration reaction, what we're going to do is try to figure out, as chemists, another way to do something useful. So here's how this is going to happen. We've just been talking about hydration, either acid-mediated or using the oxymercuration-demercuration sequence. And in both of these cases, what we've done overall is done a hydration. We've added water to double bonds or alcohols to double bonds, but we've done so with a Markovnikov orientation of our products. But what if we have to make the other way, right? What if what we have to do as synthetic chemists for whatever drug target we want to make or whatever useful molecule we want to make, what if we have to add a water molecule across the double bond, but we want it to go in the opposite direction? Just like for HX addition, where we came up with some new reagents and added peroxides and changed the mechanism and got the reverse orientation, we have another solution just like that here. It's a different solution, but it's the same concept, where we're going to change our reagents, change our mechanism, and use that to create the outcome that we are looking for. So here's what this looks like. And this is going to be called hydroboration oxidation. And just like with oxymercuration, demercuration, these words tell you exactly what we're going to be doing, right? So in our first step of hydroboration, we're going to be taking borane, BH3, and we're going to be adding BH3 across this double bond. So we have a new carbon-hydrogen bond, and we have a new carbon-boron bond, which is hydro for our new hydrogen atom, boration for our new carbon-boron bond, right? So here's our first step, hydroboration. And then in our second step of oxidation, we're going to use hydrogen peroxide and the hydroxide anion. We're going to replace this boron group with an OH group. Now, overall, if you look at our product, we're going to have added a water molecule. That's the end result. Of course, that is not the reagents that we use to do this, but that is the end result, where we've added 2 hydrogen atoms and an oxygen atom. So that's H2O, which is water. We've added it across that double bond, and it will go with anti-Markovnikov orientation. I'll show you why on the mechanism slides coming up. And it also has some additional stereochemical consequences that I'll tell you about on the mechanistic slides coming up. Before I get to that, I just want to take a moment to point out BH3 is a pretty reactive compound, so it's often found complexed with THF. I know you guys don't know what THF is. This stands for tetrahydrofuran. You don't have to worry about that. But anytime you see BH3 THF or just BH3 by itself, you can assume those are the same things, and they're going to act as if it's BH3. On paper, we can use this as if it's BH3. In real life, we have to do some things to help stabilize our BH3, but on paper, we can just write BH3. So this process, before we get into the mechanism, I just want to take a moment to say that this process, these reagents and this mechanism, all this stuff was figured out and discovered by a really famous chemist at Purdue University named H.C. Brown. And the power of this reaction, it might seem simple and straightforward, but the power of the way that borane adds across this double bond and the anti-Markovnikov orientation here and the usefulness of that came to help synthetic chemists at a time where there was no other way to do this. There wasn't even a bad way to do this. There's just no other way to do this at that time, to add water in an anti-Markovnikov fashion. And so not only did Brown come up with a way to do this, but he came up with a way to do this that works really well. It works in all sorts of different scenarios because these reagents are very specific to reacting with a double bond. And it has these stereochemical benefits as well. And so it turns out that this reaction that Brown came up with is so useful and so powerful that he actually got the Nobel Prize for coming up with this chemistry back in the 70s. So without further ado, let's look at how this works. Here is the first step of this reaction in a mechanistic sense. This is the hydroboration step. And so before we look closely at the details of what's going on here, I'm asking you guys to remember and remind yourselves what BH3 is like. So think back to your chapter 1 details and your Lewis dot structure. Boron is in the third column of the periodic table. It's only bringing in 3 electrons. These hydrogen atoms are only bringing in 3 electrons. So BH3 only has 6 electrons. Like the whole molecule only has 6 valence electrons. And so boron has an unfilled octet. It has 3 sigma bonds to each of its 3 hydrogen atoms, and then it has an empty p orbital. Now, even though BH3 is a neutral overall molecule and does not have a formal charge, because of this empty p orbital, BH3 is very electrophilic. And so, as you might imagine, being in chapter 8, where we're talking about alkene reactivity, the pi bond electrons are going to act as a nucleophile. Those pi bond electrons are going to reach out and they will form a new bond with the empty p orbital on boron. Now, at the same time that they are reaching out to form that new bond with that empty p orbital, you can imagine that that's going to leave behind a little bit of a positive charge on whatever carbon's not involved in making that bond. And so that induces the boron hydrogen sigma electrons of one of the boron hydrogen bonds to reach over and form a new bond with that left out carbon. Okay, so what am I talking about here? All of this is happening actually at the same time in concert. It is a concerted reaction. And so that means we are breaking our pi bond, breaking our BH sigma bond at the same time that we are forming a new carbon boron bond and forming a new carbon hydrogen bond. However, it does have some buildup of charge density in different states at different places. And so the boron ends up keeping more of a delta positive charge, right? Meaning that this carbon boron bond is more made than this boron hydrogen bond is broken. This pi bond is more broken and this CH bond is less made. And so what all of this does is put a delta positive charge on the carbon that is diagonal from the boron, right? So this carbon boron bond is more made than broken, and this BH bond hasn't been broken all the way yet. So this boron has a delta negative, the diagonally opposite carbon has a delta positive, and that delta positive is what dictates the regiochemistry of BH3 addition. That delta positive has to go on the more substituted carbon because that will help stabilize that delta positive. And so even though it's possible to draw out boron adding, to the more substituted side and borine coming in this orientation, this does not happen because the delta positive carbon would end up on the less substituted carbon of the double bond, and that's no good. So this less stable transition state is higher enough in energy that you do not see it happen. What you see happen is the more stable transition state where the boron goes on the less substituted side of the double bond and the hydrogen goes on the more substituted double bond. And again, this happens because we're going through a concerted transition state where we are making and breaking these bonds all at the same time. And so all of that mechanistic detail dictates that the boron goes to the less substituted carbon, the hydrogen goes to the more substituted carbon. Okay, these bullets here just say everything that I just said over the course of talking through this slide, so I'll let you review those bullets on your own later. But this borine adding across that double bond is the end result of the hydroboration step. Again, here's a hydrogen and here's a boron, so we've got a hydroboration of that alkene. Okay, so what happens then? Oh, before I go to what happens then, one thing I want to point out is that our borane reagent, BH3, has 3 BH sigma bonds. So it turns out, and this is really useful, every molecule of BH3 can be used to process 3 separate molecules of alkene, right? So our first molecule of alkene will nucleophilically attack at the same time that hydrogen transfers to the other side. So we've added B across one side of the double bond and H across the other, new carbon hydrogen bond, new carbon boron bond. But we still have two more BH bonds on our borine. And so we can get a second molecule of our alkene and do the same thing with the second BH bond. So we now have two alkyl groups attached to our boron and one BH bond left over. And then we can do it again with a third alkene. So this BH bond will be added across this double bond to get a trialkyl borane. So this is another reason that Brown won the Nobel Prize, is because BH3 is cheap, economical, easy to use, and every molecule of BH3 can process 3 different pi bonds. Okay, so the oxidation step, once we've done the hydroboration step, so here's our hydrogen, there's our new carbon-boron bond. The oxidation step looks like this. We are going to take hydrogen peroxide, sodium hydroxide, and then water. And what that does effectively is changes out this carbon-boron bond for a carbon hydroxyl bond, right? So now we've swapped out our BH2. We've installed an OH group where that BH2 group used to be. I'm going to show you the mechanism of how this works over the next couple of slides, but I want the more important point here, much more important than the mechanism of how this works, is that when you put these reagents in with your hydroboration product, you get an OH group replacing your carbon-boron bond. And the other really key feature here is that the orientation of the water that's added is an anti-Markovnikov orientation, right? So we have now added, here's a hydrogen, and here's a second hydrogen, and there's an oxygen. So that's H2O that we've added across what used to be a double bond. And the OH in this case is on the less substituted double bond, which makes this an anti-Markovnikov orientation. I want to be clear about this. This still follows fundamental principles in terms of how this reaction works. We built up delta positive charge over the course of this reaction, and that delta positive charge was still on the more substituted carbon. So we are still using our fundamental principles. This is still rational. It is still logical. It is just that we chose very carefully some reagents that gave us an end result that is anti-Markovnikov. Okay, so like I said, I'm going to show you the mechanism for the oxidation step. You do not need to know this mechanism. I'm going to say that again. I am never going to ask you to push these arrows or tell me exactly what the electron flow looks like here. I am going to use 2 slides to show you how this works because there are some intermediates involved and your book talks about them. And it's just, I don't want anyone to be confused when they run across these things in your book. So I'm going to show you how this works, but this is not something that you need to memorize. This is just to help kind of nail down these concepts in your own heads. All right, so for the oxidation step, I told you we're going to use hydrogen peroxide and sodium hydroxide. And so the first thing that's going to happen is our hydroxide from sodium hydroxide is going to deprotonate our hydrogen peroxide to give us this hydroperoxide ion. That hydroperoxide ion is a nucleophile. It can attack our trialkyl borane. So this is what this trialkyl borane is what happens when our boron has already processed 3 double bonds here, right? So this is our trialkyl borane. Our hydrogen peroxide is going to attack into the empty p orbital that is still there on this boron because it still only has 3 bonds and an empty p orbital. When we get to this intermediate, this is a kind of weird step here. One of our boron carbon bonds can actually migrate over. So the boron carbon bond is going to break, and the electrons that was holding that whole carbon substrate to the boron, they're going to jump over to the oxygen next door. It's going to basically, this is like an alkyl shift or a hydride shift that you guys have seen before. And this alkyl shift will result then in breaking this oxygen-oxygen bond, which is a weak bond, and so it's easy to break. And so this shift over is going to create a new oxygen carbon bond. It'll return an empty p orbital to boron. There will be an OH minus leaving group. This is called a borate ester. And so overall here, what we've done is we've taken a boron carbon bond and we've essentially stuck an oxygen right in the middle of that. So we've now got a boron oxygen carbon. We had 3 substrates on our boron, so we're going to do this 2 more times and basically go through the same sequence in this bond and in this bond. So we're going to get to a trialkyl borate ester. So we've inserted oxygen into each of our boron carbon bonds. And then once we get to that trialkyl borate ester that looks like this, we have more hydroxide around, and that hydroxide can basically displace each of these one by one so that we get off our OR minus, which can then be protonated to give our alcohol product. Okay, so again, you do not need to understand, well, you don't need to know and be able to show me these arrows. I'm showing you these to help you understand. The important part for you guys to understand is that when you treat your hydroboration product with hydrogen peroxide and OH minus, that you replace that boron carbon bond with a hydroxyl bond. I'll drive that home in the next slide as well. So the last thing that I want to say about hydroboration oxidation is that this reaction is a concerted reaction in the hydroboration step, right? We saw that you're forming a new carbon boron bond. At the same time, you're forming a new carbon hydrogen bond. And at the same time, you're breaking your pi bond and breaking the sigma bond between boron and hydrogen. This has stereochemical consequences in that because all of these bonds are making and breaking at the same time, we have a transition state that forces the boron carbon bond that's being made and the hydrogen carbon bond that's being made to be being made on the same side of that pi bond, right? So if we think about our pi bond as being a hot dog bun above and below, our BH3 is only going to interact with one side of that hot dog bun. And so both our new carbon boron bond and our new carbon hydrogen bond, after we finish making and breaking all of our bonds and go through our transition state to our hydroboration product, our boron carbon bond and our new carbon hydrogen bond are on the same side of where that double bond used to be. So I've shown our BH3 coming in from the bottom face of this double bond. It could also come in from the top face, but if it comes in from the top face, then the boron and the new hydrogen bond would both be on the top face of this double bond. Okay, so this is referred to as syn addition, where our 2 new sigma bonds are going to end up on the same side of that pi bond. When we oxidize this boron, when we do our oxidation step using hydrogen peroxide and hydroxide ion, that carbon boron bond is replaced with a carbon hydroxyl bond. But part of why I went through those last 2 slides of the mechanism is to show you that this carbon never changes. The orientation at this carbon does not change in that mechanism. We're not ever using, attacking at this carbon. And so the stereochemistry of this carbon boron bond is conserved and stays exactly how it is when that boron is replaced by an oxygen. So what we've done in our hydroboration oxidation sequence is that we've actually created 2 chiral centers in this case, in the case of this molecule. We've created them very specifically in an orientation relative to each other. Okay, so we've created 2 new chiral centers. We've done our BH3 addition because it's concerted. It's a syn addition where they both the boron and the hydrogen end up on the same side of the double bond. And when we replace our boron with an oxygen, that doesn't change that orientation. So overall, our water molecule that we've added, our OH and our H, are on the same side as each other of this double bond. Now, like I said, we have no way of differentiating the 2 sides of the hot dog bun. So our borane is going to add to the bottom half 50% of the time. It'll add to the top half 50% of the time. So we will get a 50-50 mixture of both enantiomers. The other enantiomer is what would result if our borane sat down on top of the double bond as we have it drawn here. In all cases, we are still putting the boron carbon bond on the less substituted side, right? Our regiochemistry is the same in all these cases. Our carbon boron bond will be on the less substituted side. So therefore our carbon-oxygen bond will be on the less substituted side in an anti-Markovnikov fashion. But overall, what we've done is this anti-Markovnikov hydration, right? We've added water across our double bond in an anti-Markovnikov fashion and in a syn addition. So both on the same side of that double bond. Okay, so in the last 2 minutes of class, I want to show you just a couple of slides to introduce you guys to halogen addition. And we'll talk more about halogen addition and extended halohydrin formation on Wednesday, but I do want to give you guys a flavor of halogen addition. So here we go. When I'm talking about adding halogens across the double bond, I'm talking about X2, so molecular bromine, Br2, or molecular chlorine, Cl2, sometimes iodine. This is going to add across the double bond to give you one atom each of the halogen on each of your carbons that used to be the double bond. This is going to add in an anti-addition, which I will show you on the slides coming up mechanistically. So when we're talking about molecular halogens, so Br2 or Cl2, this bromine-bromine bond is fairly weak. And as you can imagine, it's pretty much okay with the bromine if it leaves with these 2 electrons as a Br minus. And so that means that a nucleophile can attack either of these bromines. The end result is the same because it's a symmetrical molecule. But the nucleophile will attack at one side of this molecule, form a new nucleophile halogen bond, and then the sigma electrons holding those 2 halogen atoms together will leave with the halogen as an X minus. So you can see we can do that with an oxygen nucleophile, right? To get this new oxygen bromine bond and a Br minus. We can do it with any nucleophile. So we can do it with ammonia to get a nitrogen chlorine bond and a Cl minus. When we do this with an alkene, it works the same way, except that in an alkene, when you use these pi electrons as a nucleophile, which remember is like our typical way of reacting alkenes, is to use these pi electrons as a nucleophile. When we do that, and we use these pi electrons as a nucleophile, we're still going to break this bromine-bromine sigma bond. We're still going to send those 2 electrons with Br as Br minus. But in doing this, we would have created a positive charge on the carbon if we had just followed these simple 1 arrow electrons. But that bromine has this double bond right there. And so it's going to use lone pair right there, and it's going to use one of the lone pair electrons to form a new sigma bond. So when we do this pi bond nucleophilically attacking our bromine, we end up with a 3-membered ring called a bromonium ion, the same type of intermediate that we saw from oxymercuration, where when we attacked our mercury ion and that mercury ion had a lone pair, it could then create a 3-membered ring. Now, as you can imagine, we've also generated this really good nucleophile, Br minus. And so the lone pairs on this Br minus can go in and attack our now electrophilic carbon and break our new carbon-bromine bond and create an anti-addition product of bromine across that double bond. So I'll talk more about this on Wednesday, but before I let you guys go, I want to show you one more thing, and I'll post these slides. Your book has a chart 8-1, that shows an overview of all the different types of addition reactions that we're going to learn about this chapter. We've done hydration, we've done HX addition, we just started halogenation, and halohydrin formation is going to follow up halogenation pretty quickly. What I think would be really helpful for you guys is to use this chart as a study guide. So you can use this chart to go through your notes and slides and think about for each one of these things, what are the reagents that you know how to do this? Are there more than one way that you know how to do this? What is the stereochemical outcome, or what are the consequences for each of these reactions? And I think that this is so useful that I want you guys to each build your own chart for the details of these key reactions, and you will have an opportunity to turn in your chart for extra credit. And I think this is so useful that I made you a scaffold for your chart, where I took the chart from the book, and sometimes, like in HX edition, you guys know 2 ways to do this, even though on your book's chart it's only showing one time because it's one version of overall. but you guys know 2 different ways to do it that have different outcomes and different reagents and different intermediate to transition states. So this type of chart I'm going to release for you guys in Canvas, and I really strongly encourage you to start filling it in and use it as a study guide. And I'm going to give you extra credit for doing this and uploading it, but I actually think the real benefit is going to come from you guys filling it out and learning as you're filling it out. It will probably be due on Monday of next week, but I will post some announcements and we'll talk more about it on Wednesday. You guys only know how to fill out these top 2 rows here right now. This 3rd row is where we're starting right now. So this is actually a 2-page chart, not just a 1-page chart, but a 2-page chart. And you guys only know how to do these top 2 rows so far. So I encourage you to go ahead and start filling it out with what you know so far. But we'll talk more about it on Wednesday, and I'm going to let you guys go because I'm over time now. Thank you guys.
Thank you. Have a wonderful day.
Thank you, you too.